All right, welcome everyone. Here we have another kind of reasonable exam style question or quiz style question, something to be done in a timed assessment. We're interested in finding the work done by this vector field here. In this case, we haven't given it a name. You can call it F or G or whatever you'd like here. And moving a particle along the triangle, let's see, from this point, 1, -1, 0 to 1, 1, 0 to 0, 0, 1, and then finally back to where we started at 1, -1, 0. So here's kind of the picture that we're going. Here's where we start at 1, -1, 0, second, third, and then back to where we started, fourth, right? And so again, we're interested in finding the work done for this, and I claim, right, this is in a video that's called 16.8, right, Stokes Theorem. Notice in this problem, it does not say Stokes Theorem. In fact, I don't even see an integral sign. So there's a little bit of interpretation that we have to do before we even, get to the calculation bit. So first of all, we have to remember, find the work done. Finding the work done by a vector field, this comes down to doing a line integral of f dot dr. So maybe if we call this our vector field f. Even then, this notation, the ijk notation is okay. I usually like writing it in the kind of the explicit vector notation. So in the I component we have z, in the j component we don't have any j's, and in the k component we have y. So I would prefer to see the vector field given as z, 0, y, but they don't always do that, and we need some practice then. Okay, so here's the vector field. We're interested in the work done by this vector field and pushing it along this triangle. Notice if you wanted to calculate out the line integral, this is certainly an option, calculating out the line integral, but there are three pieces. We would have to calculate out the line integral along this piece, right? We'd have to parameterize that, figure out our dr, all that good stuff. Then we would have to do this piece, right, another line segment, parameterize that line segment, calculate out its derivative, right, its dr, do the dot product, do the evaluation, all that stuff. And then finally we would have to do the third piece, right, do its parameterization, make sure that you're going in the correct direction, take its derivative, take its dot product, all that sort of stuff. So you'd have to do these three calculations, one for each piece of this triangle, because you have to parameterize them all individually. And so we could do that. It would take some time, but it's possible. The claim is there's a better way thanks to Stokes Theorem. So again, Stokes Theorem says if you have a line integral, you can decide to trade it in for a surface integral. And that the surface integral is going to be over the surface, right? The only condition really is that C needs to be a boundary curve. But instead of just f, you're going to have the curl of f. So it's the curl of f dot ds here. And in this case, kind of the most natural surface that has the boundary curve C is going to be the surface that's inside of this triangle, right? And this is probably some piece of a bigger surface. In fact, it looks like kind of a flat surface, so it's probably a piece of a bigger plane. So maybe there's some bigger plane, and we have just the piece of that plane inside, bounded by this curve. So again, this is now Stokes Theorem. This is how we're using Stokes Theorem here to help make our life a little bit easier. And the claim is instead of three line integrals, we only have to calculate out one surface integral, right? Because it's just one surface here. All right, so let's get to work here. We need the curl of f. So let's kind of pull off to the side here for a second and figure out what is the curl of our vector field. So remember, for curl, it's going to be the determinant of a 3×3 matrix. Here's our del operator, partial with respect to x, partial with respect to y, partial with respect to z. And then in the final row, we put our f. So again, this is z, 0, y. That's our f up here. Whenever we take the cross product, right, we're going to have stuff with i's minus stuff with j's plus stuff with k's. And our stuff with i's, right, okay, let's go ahead and cross off that first row and first column. We're going to have the partial derivative with respect to y of y minus the partial derivative with respect to z of 0. It's going to be 0. All right, let's go ahead and cross off that first row and now the second column. Partial derivative with respect to x of y minus the partial derivative with respect to z of z. And then finally, the first row, third column, partial derivative with respect to x of 0 minus partial derivative with respect to y of z, also 0. So we're going to have 1, and this is -1, also 1, 0. So the curl of f is 1, 1, 0. All right, so let's go back here. and we're going to write, we're doing the surface integral. The curl of f is 1, 1, 0, and now we need to do dot ds. So remember, this is some notation here. This is dot, and this ds means we are going to have our normal vector, right? So we need a normal vector here. Let me go ahead, maybe in this line, I'll just write n, and then this is our regular old ds, non-bold s here. So we need to know, how do I get a normal vector for this surface, right? Remember, there's always kind of two ways to get normal vectors, either if you have a parametrized surface or if you have an explicit surface, right? Either way, you need a surface equation, right? You need to either have it parametrized or you need z equals. Well, I know it's going to be a piece of this plane, but I don't have the plane's equation. But I have 3 points. So if you have 3 points, we know how to get an equation of a plane. This is something that we brought up back in chapter 12. I'm going to admittedly go a little bit fast through this. In this case, right, these points are so nice that you could actually do a little bit of guessing and checking here and get the equation of this plane. It ends up being that this is a nice cylinder, right? So we have some line that's independent of y's, and you can just kind of move y freely in this case. And so we can get the equation x plus z is equal to 1. And we can see that this actually satisfies in all 3 points, right? X plus z is equal to 1. So if you take x plus z, that's equal to 1. X plus z, that's equal to 1. X plus z, that's equal to 1. So this equation, this plane equation, satisfies all 3 points. Remember, if you can't guess and check these ones, right, or if you can't get this one just by eyeballing it, the correct way is, right, you figure out maybe the vector. If you call this point A, point B, and point C, you figure out the vector AB, and you figure out the vector AC, and then you can take the cross product between those to get the normal vector, and then you just attach it to one of these points. That, of course, is the longer way to do it. And again, we did this in 12.5, so even if you had very nasty points, we could still figure it out. Well, let's kind of focus on the Stokes Theorem problem, or the Stokes Theorem bit of this one, and I'm going to go ahead and say that, okay, assume that we can do this, back from chapter 12, section 5. This is going to give us our z equals 1 minus x. So we're able to solve this surface as z equals, which means that when I go to find my normal vector, right, I'm going to go ahead and use the explicit form. So this is going to be the surface integral. We have 1, 1, 0, and then we're going to be dotting with plus or minus, and then we take the partial derivative with respect to x, I get negative 1. The partial derivative with respect to y, I get out 0, and the partial derivative with respect to z, well, not exactly, right? In this case, it's just always negative 1 for the third component. There's a different explicit format, right, where you're just using the gradient. If you'd like to do that, you would get basically the same result. Right, over here you would end up getting 1, 0, 1. So you'd just be facing the other direction. Either one works in this case. So, okay. Let's go ahead. We have to think a little bit about, should I have the plus or should I have the minus? So this is where we have to use the right hand rule and the fact that we're curling our fingers in the direction that we're parametrizing. And in that case, my thumb is pointing in this upward direction. So I want to have a positive z component. So if you want a positive z component, I'm going to go ahead and choose the negative sign here and distribute it to each one so that it becomes positive ones. So let's go ahead and do that. So the integral 1, 1, 0 dot, and this is going to be positive 1, 0, positive 1. And so we evaluate out that dot product, and this is just going to be the double integral of 1 dA. All right, so now we're officially doing our double integral. We're just going to have x's and y's, and so I need to know, what are we doing the double integral over? And so if you were to take this region right here, take this and smash it into the xy plane, I think you would get some triangle that looks like so, right? This is where all the residue would live, in the xy plane. It's just basically taking this point here, this 0, 0, 1, and bringing it down. So let's go ahead and maybe sketch this in the xy plane. So it looks like there's some action going here in the positive x direction. And in fact, if you were to just plot these points, right, A is 1, negative 1, and you kind of forget about 0. Again, that's already in the xy plane. So 1, -1, and then 1, 1, and now 0, 0, but you're smashing that down into the xy plane, right? You're bringing that down to z equals 0. So now it's in the xy plane, so 0, 0, you're going to get this triangle right here. So this is the region, this is where all the residue has fallen, right? After you smash this surface down into the xy plane. And so now we could evaluate out this double integral over this region. However, we recognize that it's a triangle, and whenever you have the double integral of 1 like this, that's just area, right? So we need the area of this triangle. So area of the triangle is 1/2. Maybe your base has length 2, so maybe this is my base right here, it has length 2. And my height of my triangle, well, maybe this is my height right here, my height is 1. So altogether, once you evaluate this out, you would get 1. So this is a little bit of a shortcut, remembering that the double integral of 1 is just area. Alright, so one more time, the recap here is that it said to find work. We remembered that work was given by the line integral over some vector field. When we looked at this, we said, I'd have to parameterize 3 curves. I'd have to do all the DRs for those 3 curves. This would take a long time. Maybe instead of doing 3 line integrals, 1 surface integral will be a little bit faster. So I used Stokes Theorem to trade it in for 1 surface integral. We went ahead and calculated out the curl of f. And we decided in order to evaluate outright our normal vector, we were going to use the explicit form. Remember, we have parametric or explicit. So I used the explicit form. Then I went ahead and evaluated the dot product. That gave me the double integral of 1, and I remembered that the double integral of 1 is area. So I did the area of this nice triangle here in the xy plane. So 1/2 base times height to give us our final answer. All right, so yes, this is one that actually, the evaluation, it's not too crazy, right? Sometimes these double integrals get crazy here at the end, but that's why I think that this one's, reasonable for quizzes, for exams, right? Because there's a lot of visualization and interpretation going on here, but actually the evaluation, once we actually know what we're trying to integrate, the evaluation is not bad at all. All right, so again, that's all there is to it. We got one more divergence theorem problem coming up next. I'll see you then.